Hello students, I once again welcome you back to the econometric methodology course. We had so far seen the meaning of econometrics, the methodology of econometrics and the objective of econometrics and the limitation of econometric methods. Today we are going to see the basic statistical concepts required for the econometric analysis. We call it review of statistics. In this session, I am going to discuss about the basic concepts. The first and foremost concept of statistics that would be of great use to you is the random variable concept. Many important economic variables are random variables. Though we know all possible values of the same, we do not know for sure what values they will take. We may assign a probability to each of the possible values. These kinds of variables are known as random or stochastic variables. In this lecture, we are going to discuss about the conceptions relating to stochastic or random variables and the properties of them. A random variable has 4 properties. It takes a single value or a specific value. We do not know in advance what value it is likely to take. We know the probability that it will take one of those possible values. We shall denote the random variables by capital letter in the English alphabet, namely X, capital X, capital Y and capital Z. We shall use lowercase letters like small x, small y and small z etc. to denote particular values of a random variable. Some random variables are discrete and some are continuous. So, there are 2 types of random variables. If the random variable x can assume only a particular finite set of values, then it is called discrete random variable. On the other hand, for instance, gender, educational qualifications are the random variable which are discrete in nature, because the gender takes only 2 values. The educational qualification takes only certain number of discrete values, and so these variables are called discrete random variables. On the other hand, if a random variable assume any value in a certain range, then that random variable is said to be continuous random variable. Income of a family, GDP, daily petrol price, amount of energy consumed in an hour are all some examples of continuous random variable, as these variables may take values in a range that may vary between 0 to certain big number. Now, we will discuss about the probability distribution function of stochastic variables. Every random variable associated with each random variable is a probability distribution that determines the probability that a random variable will take a specific value. This association may be denoted as an algebraic function. Such function is called probability distribution function. The probability distribution function defined for a discrete random variable is mentioned as probability mass function. The probability distribution defined for a continuous random variable is mentioned as probability density function, or in short they will call it PDF. The continuous random variables are common, the popular and frequently used in econometrics. One of the popular probability density function is normal density function. It is defined as f of capital X is equal to small x is equal to 1 by sigma square root of 2 pi into exponential minus half into x minus mu by sigma whole square, where sigma is the variance and mu is the mean of the distribution. Here x may take value from minus infinity to plus infinity. Let us see some of the properties of PDF. Let us take the probability distribution function defined in a range a to b. First, the probability is positive, that is f of x is greater than 0 where x belongs to a to b. The second property, the summation of f of x over a to b is 1, that is integration over a to b f of x dx is equal to 1. Property 3, summation over a to a1 f of x dx is greater than summation over a to a2 f of x dx if and only if a1 is greater than a2. Fourth property, summation over a to a1 f of x dx is equal to 1 minus summation over a1 to b f of x dx. Now, let us see some of the descriptive statistics defined for random variables. Similar to normal mathematical variables, we may define univariate and multivariate measures for the random variables as well. The usual summary values are defined as expectations measures in random variables. For instance, mean is defined as expected value of x. Let us say E of x is equal to summation over a to b x f of x dx. Here f of x is a probability measure and summation a to b is a summary measure like sigma. Then sigma pi xi in the normal context is the weighted average of the variable. Here each value of the variable is weighted by its probability measure, and so E of x is nothing but the mean, or denoted as mu. Expected value of x is also called the expectation of x or the mean of x and is denoted by mu of x. It is also known as first moment around the origin. Similarly, we may define variance measure for the random variable capital X. Here sigma square is equal to variance of x is equal to expectation of x minus expectation of x whole square. This may otherwise written for a continuous random variable as summation x minus mu of x whole square f of x dx, the variance measure defined for a random variable. Probability weighted average of squared deviation. It is a second central moment. Moments are simply the expectations of different powers of the random variable x. For example, expectation of x power r is called the rth moment. The first moment is mean, obviously. Expectation of x minus mu whole power r is called the rth central moment. The first central moment value, expectation of x minus mu, is 0, but the second central moment, expectation of x minus mu whole square, is the variance. The expectations may also be defined for any arbitrary function. Say for example, expectation of g of x, where g is a arbitrary function of capital X, is equal to integration over a to b g of x f of x dx. Here note, expectation of r is called the rth moment. The first moment is mean, and expectation of x minus mu whole power r is called the rth central moment. The first central moment is 0, but the second central moment will provide the variance. Let us see some of the properties of the expectation measure. If a, b and c are constants, expectation of x plus c is equal to expectation of x plus c, since expectation of c is equal to c. Second property is expectation of c multiplied by x is equal to c multiplied by expectation of x. Third property, the algebraic sum of x, namely expectation of a x plus b is equal to a into expectation of x plus b. Similarly, the expectation measure defined over two random variables x and y. Expectation of x plus y is equal to expectation of x plus expectation of y. If there are arbitrary number of random variables, the expectation of sigma a I capital X I is equal to sigma a I into expectation of x I. For random variable, we may define bivariate and multivariate summary measures also. Many economic problems involve dealing with more than one variable at a time. In those cases, we are often interested in joint variation of pair of or more than two random variables. There are likely joint occurrences and probabilities. They are represented by the joint probability distributions. Let x and y be two random variables. Then x, y have joint distributions which are fully described by the joint probability density function of x and y. This is denoted by f of x, y. F subscript capital X, capital Y of small x, small y is equal to probability of capital X equal to small x, capital Y is equal to small y. Now, let us define marginal density function for the joint probability density function. Given the probability of joint probability density function, a marginal density function may be obtained for each variables. It describes the probability density function of an individual variable. It is obtained by summing out or integrating over the range of other variable. For example, in the joint probability density of f subscript capital X capital Y of x comma y may be defined as f subscript capital X of x comma y is equal to integration over a to b f of small x small y dy. Conditional probability density function may also be defined for a joint probability density function. Conditional probability of a particular random variable given a value of another random variable. The symbol vertical bar stands for given. The conditional probability density function is f subscript y given x of x comma y is equal to f subscript capital X capital Y of x y by f subscript capital X of x. Now, we will see some of the summary measures of association using this joint probability density function. While the joint probability density function of two random variables completely describe the relationship between the variables, it is useful to have a summary measure of how on average two or more random variables vary with one another. Covariance measure is an important summary measure of association between two random variables. The covariance between two random variables x and y concerned with the relationship between two variables. It is defined as the expected value of the product of capital X minus mu x into y minus mu y, where mu x and mu y are the expected value of capital X and capital Y respectively. Covariance is denoted by COV of x comma y or sigma subscript x comma y. Let us define it. Covariance x comma y is equal to sigma x y is equal to expectation of x minus mu x into y minus mu y. Covariance measures the amount of linear dependence between two random variables. Other association measures like regression coefficients may also be derived from this. The idea of covariance is also important in the statistical inference. Properties of covariance. Property 1, covariance of x comma y is equal to covariance of y comma x. If x and y are independent, then covariance of x comma y is equal to 0. Property 3, covariance of ax comma by is equal to AB covariance of x and y. Fourth property, for any constants a1, b1, a2 and b2, covariance of a1x plus b1, a2y plus b2 is equal to a1 a2 covariance of x and y. Fifth property, for any constants a and b, variance of a x plus b y is equal to a 2 variance of x plus b 2 variance of y plus 2 a b covariance of x and y. So far we have seen the meaning of random variables and the summary measures defined over the random variables. First we saw the univariate summary measure like mean and variance on random variables. Then in the later part we saw the associative measures defined on the random variables. Okay, now let us summarize what we have studied in this session. First we saw the meaning of random variables, followed by the summary measures defined over the single random variables like mean, variance and moment measures. Then we saw the summary measures defined over the relationship between two random variables, namely covariance measure. In this session we saw certain symbols quite often used in the conduct of random variables.